Now we're going to talk about the dimensions of a sine wave. They include amplitude, frequency, period, phase, and wavelength. Our first discussion will be on amplitude. Amplitude is a measure of the strength, or the magnitude of the sine wave, and it's also referred to as the sound pressure. So going back to that balloon example, as the balloon moves outward, the air molecules immediately adjacent to the balloon surface are pushed outward from their resting position, which results in increased density, also known as compression. As the balloon begins to deflate, the molecules move back towards their original position, but there are fewer molecules in the immediate surface area of the balloon, and we have a region of decreased density, also known as rarefaction. The individual air particles are displaced sinusoidally over time. The amplitude of the displacement varies sinusoidally over time. A maximum displacement corresponds to both 90 degrees in the positive direction and 270 degrees in the negative direction. The magnitude of particle displacement, however, is difficult to measure. But if we think about the derived quantities that we described in Chapter 1, we can better understand it. So with amplitude, we're going to talk about the relationships among displacement, velocity, acceleration, and pressure. The particles are moving with some speed, but because of the direction of the movement is changing, the velocity of the particle displacement is also changing. Remember that velocity incorporates both the magnitude of displacement and the direction. When displacement is maximal, velocity is zero, and motion is momentarily halted. When displacement is zero, and the body is moving through equilibrium, velocity is at its maximum. So if particle velocity is changing, then remember the particle must be undergoing acceleration either in the positive or the negative direction. The particle is accelerated as it moves from maximum displacement towards equilibrium, and it's decelerated as it's moved away from equilibrium towards maximum displacement. Therefore, particle velocity leads particle displacement by 90 degrees. Particle acceleration leads particle velocity by 90 degrees. Particle acceleration, therefore, leads particle displacement by 180 degrees. So why does acceleration lead displacement by 180 degrees? It goes back to Newton's second law of motion. Force equals the product of mass and acceleration. Remember Hooke's law? The elastic restoring force is directly proportional to the magnitude of displacement. So in sinusoidal motion, we have two opposing forces, the inertial force and the elastic restoring force. And Newton's third law of motion stated that for every force, there is an equal and opposite force. So the force of inertia equals the restoring force. And if you remember, the force of inertia is mass times acceleration. The restoring force is the spring constant times displacement. You have two constants in the particle, their mass and their stiffness. And you have two variables, the acceleration and the displacement. Since the Fi equals the Fr, the two variables, acceleration and displacement, must be opposite one another. As the balloon surface moves outward and inward, the number of molecules per unit volume, the density of the medium changes over time. and the pressure in the medium is related to the density of the medium. Thus, there will be changes in air pressure that also occur sinusoidally over time. The pressure waveform mirrors the particle velocity waveform, and both are shifted by 90 degrees relative to the particle displacement waveform. Lastly, we're going to talk about instantaneous amplitude, and how to measure amplitude. So we have instantaneous amplitude, maximum amplitude, peak-to-peak amplitude, and the most effective measure of measuring amplitude, the root mean square amplitude. Instantaneous amplitude is not very useful. It's the amplitude of particle displacement at a given moment. Maximum amplitude, sometimes called peak amplitude, is the instantaneous amplitude at 90 degrees or 270 degrees. The peak-to-peak amplitude is the absolute difference between the amplitudes at 90 degrees and 70 degrees. The most effective amplitude is the root mean square amplitude. This is the standard deviation of all the instantaneous amplitudes in a sine wave, and we square the deviations to remove the algebraic sign. All the values become positive, and the problem is solved. So let's look closely at this waveform. We could take an instantaneous amplitude at 2, 4, positive 2, negative 2, negative 4. But we know in general the wave undergoes a lot of different amplitudes. So to say that the amplitude of the wave is 4 is inaccurate. Or to say that the peak-to-peak amplitude, that's not accurate either. What we really need to do is find an average amplitude of this waveform, or an average pressure, an average strength of this waveform. And to do that, we have to knock out the negative numbers. So we square all the values to remove the signs. We sum these values. We divide by 6 because we took 6 points. And then since we squared everything, we have to take the square root to get a valid answer. And the square root of this is 2.828. And that's the root mean square amplitude. That's the average amplitude of the waveform. And that's most useful for us.